Okay, let's look at this one and then we'll move on. So there. So this one says that a drill with radius 5 is used to bore through a hole through center of sphere of radius 9. Find the volume of the ring-shaped solid that remains. This is like a napkin holder, right? This is like exactly what a napkin holder would be. It would be like a sphere with a cylinder drilled through it. Okay. So how do we take what we're learning about double integrals and apply it to this situation? So what does a double integral find? Volume, right? Or sine volume, right? It could find volume as long as we've got a positive z surface, if it's always positive. All right, so we're thinking about what surface do we need and what scenario do we build in R3 that we would evaluate a double integral and that would be the answer to this problem. Right? Because double integrals are about something in R3 with a projection into R2, right? The region projection in R2. So what scenario are we going to set up here to create this thing so that a double integral would get us the volume? Was she first? I saw 3 hands. All right.
We should make our function a sphere.
He wants our function to be the sphere. Sphere of radius 9. Something like this. Oh, I was doing so good until then. This, that, something like that. That's a half sphere. That's what that is. Okay. All right. Okay, so something like this, and then so what's the equation of that? So we're all experts at this. What is it?
Plus y squared plus z squared equals.
Right. So we want to make it as easy as we can. 3 squared, right? Oh no, 9 squared. So make it as easy as you can, right? Put the center at the origin. We know the radius is 9. We know this is our easy equation of a sphere, center at the origin. Okay? And so then we also have, what? We want to drill radius 5, and so we're going to drill this vertically. So we're going to have something like this. That's going to drill a hole right out of that thing, okay? So then how does this relate to a double integral, right? So then how do we set up a double integral that's going to reflect this volume outside of that cylinder, but below the sphere, right? And above the xy plane. That's what we're talking about. And then we can just multiply the whole thing by 2 in the end, right? So I need a double integral. So there's 2 aspects, right? There's our integrand. And of course there's dA. And then there's the region, right? So there's what's going to be, what are we going to integrate? And then what's our region going to be, which is going to determine our bounds, right? Our bounds. Okay? So what are we going to integrate? So what is that thing? I know that
The sphere minus the cylinder.
the sphere minus the cylinder. Agree with that? Yeah.
It's just the sphere, but the next part I'm going to see is with the balance.
Yeah, so does the cylinder have to do with the integral part, or does it have to do with the region? Yeah, so the sphere it kind of limits what the region that we're integrating over is, right? So this kind of donut shape here, down here on the xy plane, that's where the cylinder's going to come into it. Because instead of integrating over the whole disk, we'll integrate over the ring, right? Like the washer. So since this is in the xy plane, this integrand is really only the sphere, right? So we want the volume under that sphere down to the xy plane. And then over that region, the ring region, which is D. So this ring region is our D. And so that's where the cylinder comes into it. So what are we going to integrate? X squared plus y squared plus z squared? No? So in general, what is this right here? What value is this? Z, right? That's a z value, right? Surfaces are z as a function of x and y. Surfaces are defined as z is a function of x and y. So z is what? Square root of? Can I fit it? Yeah, of course I can. All right. Make sense? So z is, the surface is, as a function, is square root of 81 minus x squared minus y squared. That's the top of the half sphere. And so now d. So we look at d, and it's this. And so do we want to use type 1 or type 2?
Polar.
Oh, you got me. For sure polar, right? This is in the polar wheelhouse, right? This is in the wheelhouse for polar, right? What is this radius here? From 5 to 9. So in polar coordinates, this is super easy, right? So what do we do first? So dA becomes r dr d theta. R goes from 5 to 9. S theta goes from? One last thing to change here. 81 minus r squared, because r squared is x squared plus y squared, so minus x squared minus y squared is minus r squared. What happens to the r? It links up with that function, right? The r comes to the party with dA, but then it joins up with the integrand. So then that's, how do we do that antiderivative? R times square root of 81 minus r squared. Okay, so if you learned U substitution, or if you had me, we can do it a lot faster than U substitution, right? We recognize that this is the result of a chain rule derivative, right? Because that is essentially the derivative of the inside. R is essentially the derivative of r squared. So we just do 81 minus r squared to the 3/2. We need a 2/3. We need a 1/2. And we need a negative, right? A lot faster than U substitution once you learn how to do that. And then we're going to evaluate that from 5 to 9. That'll give us just a constant. That's just going to give us a number because there's no thetas in there. And then we'll end up multiplying that by 2 pi. Is that right? If we do that thing d theta, it'll just be that times theta, and then it'll just be times 2 pi. So it'll be that whole thing times, I'll just write it, 0 to 2 pi. D theta. And then that whole thing times 2, because we only did the top half, right? So I went fast, but you thought about it, so hopefully that made sense. Any questions on that problem? Last chance. Yes, please. This two, the big 2 in front? Because I just did the top half of it. So remember, so the question is a whole sphere, and we're going to go all the way through. So I just found the volume above the xy plane. So it'll be symmetric to the volume below, so I can just multiply by 2. Ask if I didn't. Important problem, right? So this is really, really important problem. Okay, so we are experts at double integrals, right? Which means that we are almost experts at triple integrals. Question, yeah?
when we choose dr instead of d theta and d theta instead of dr, or like the switch positions.
It'll always be r first and then theta.
I did it for one of the questions instead of r.
Oh, they switched in one of the web work. It switched the order. Does anyone know what number that is? Number 1? All right, let's see. Well, you got 100% on it. Oh, I see. Okay, so here's the deal. Because of all the constants, or all the limits of integrations are constants, there's no functions involved, right? So r could be a function of theta, and then r would have to be first, the inside. But since these are all constants, the r values are constants, and the theta values are constants, whenever you have a double integral where your bounds are all constants, it's totally interchangeable. But the way we want to think about these is always r first and then theta. I think is easier. But so you just look at this. Yeah, so they're just switching it just to see if you recognize that it can be switched. It's nothing profound at all. When you have a double integral, all your bounds are constants. It's just you can just switch it without any thinking. You can just switch it. That's all there is to it. Other questions? But in terms of setting up, like the problem we did, whenever you're going to set up an application problem or set up a double integral, just always do r dr d theta. Okay, here we go. Okay, I hope this is right here. All right, so like I said, since you guys are experts at double integrals, you're almost experts at triple integrals. We just have to, you'll see. So the way that we want, here's the triple integral. So the function that we're integrating now could potentially be a function of 3 variables. So let's just review our functions of 2 variables. How did they relate to geometry? So when we had a function of 2 variables, what was that? In what dimension? And how does it graph? So what is that? In what dimension? How does it graph? So any volunteers? Yeah, Paul?
It's the surface in R3.
It's a surface in R3. Values of z are a function of where you are in the xy plane, right? You pick a point in the xy plane, that's like the input. The independent variable is like a point in the xy plane. The function tells you the particular z value associated with that point, and you get a height above the xy plane. Put all those points together, you get a surface, right? So what would this be? So then we gotta just take that. So let's talk about the independent thing. The independent variable is what? Where does it live now? The independent thing is what? What is the independent, or the thing going into this function? A point in R3. So our launch pad for the independent variable is R3. Okay, so a point in space now. And then what does this graph? Yeah, something in the 4 dimensions, right? So the point from the independent variable is a point from R3, and then the function assigns that to something in, it's what we call a hypersurface, right? So it's like a surface in R4, whatever that is. There's different ways to try to depict that. But it's not convenient or comfortable because we live in R3. We don't live in R4, right? So anyway, so this is now going to be. We can think about where the input comes from. The input comes from R3, and then the output is a surface in R4. So that's kind of what we're getting at. So then, so what are we integrating over then? When we do a triple integral, in general, so with a double integral, we were integrating over a region in R2, right? A region in R2. So now with a triple integral, we're integrating over what? Solid. So we'll call solids E. So curves are C, regions are D, and solids are E. So we're integrating over a solid, meaning we're accumulating all the values of the function for all the points in this solid that live in R3. Okay, so now we talk about how do we think about setting up approaching triple integrals. That's kind of the groundwork. How do we think about them? Well, we don't think of them as three integrals. Here's how we think of them. We first think about it as surface to surface. So we have this solid in R3 that we're integrating over. And so we're going to think about the inside integral is going to be like surface one side of this to another side of this solid. Okay? And then we think about an outside, the remaining part of this is a double integral. And that's the double integral of how the solid projects into one of the coordinate planes. So you're going to take that solid E and you're going to project it into either the XY, the YZ, or the XZ plane, and you're going to get a region. And so now this outside double integral is for the region, just like we've been doing double integrals. Okay? So that's why I said if you're expert at double integrals, you're almost an expert at triple integrals, because every triple integral involves a double integral of some region in one of the coordinate planes, either the XY plane, the XZ plane, or the YZ plane. So don't think of this as a three-step process, think of it as a two-step process. Surface to surface, and then outside double integral for the region as it projects into the whatever plane you're talking about. So really we get, so that's our D, right? That's our D. So really this kind of breaks down into three different types then. This is going to be type A. So with type A, the inside double integral is going to be termed as Z. So notice the dV just became dZ. So in your notes, you're going to have to write this over and over again. I'm going to keep replacing things on that. You're going to need to write this several times. So this is type A. Type A is where you first do what? Surface to surface. So if it's dZ, we're doing the bottom surface, which is some function of x and y, h1, x and y, to the top surface, which is some other function of x and y. It's always surface to surface and then the outside double integral. For type A, you're talking about going from the bottom surface, integrating up to the top surface. And then your outside double integral is for the projection into which plane? XY plane. So however that solid, that blue-green solid, however that projects into the XY plane, that makes a region, and your outside double integral is now just like a double integral that you've done in the XY plane. You've got two choices, type 1 or type 2 or polar. Right? You can do type 1, type 2, or polar for that outside double integral. So that's type A. So what is type B? Type B looks like this. So if we're talking about from surface to surface, from which surface to which surface? So first of all, the type B, our inside double integral has a order dx, right? The integration variable is x. So we're going to go from what surface to what surface? back to front, right? So it's going to be back, a function of y and z. So x is a function of y and z, the back surface here, to the front surface here, which is also x as a function of y and z. Then what's the outside double integral? The outside double integral is for the projection into the, this is the projection back here into the YZ plane. So however that thing E, its shadow, the shadow of E into the YZ plane gives us a region. That region will define how we do the outside double integral. So type B is back to front, and then do the double integral for the projection into the YZ plane. Is this making sense? So then what's type C going to be? Can you, so first of all, what will be the inside variable for type C? What will the variable be? Right, so it'll look like this, and the variable will be y. We'll start with dy, and it'll go from what to what? Left to right. So the left surface will be some y as a function of x and z. It's the left. And the right surface will be another function of x and z. So we start by going, what, left to right. And then the outside double integral will be for the d projected in the xz plane. That's our type C. So how many types of triple integrals are there? Someone said it? 9, right? But it's not, you don't have to think of 9 different ways to do it because you already know double integrals. So you just really have 3 new things to think about. For each of those 3, you have the 3 possible double integrals. Type 1, type 2, or polar. So you have type A, type B, and type C, and in each of those, for your outside double integral, it could be type 1, type 2, or polar. So for instance, in type C, what is our order of integration? That's what we before would have called type 1. So if this is the xz plane, in type Z, so type C, and then if the outside double integral is type 1, what would that be? It would be? What came first, vertical or horizontal? In type 1. Vertical. So it would be dy, then dz, dx would be type C1, for instance. So C1 would be dy, and then 1 would be what? Vertical, a vertical strip, and then accumulate all the vertical strips horizontally. So that'd be dy, dz, dx. That'd be C1. Yeah?
So if you wanted to do polar coordinates,
Yeah.
would you first solve the surface one and then change the thing around to polar, or just change it to polar first?
You're talking about this?
Yeah.
So that, let's hold off and think. We won't get into polar until. Yeah, let's just don't worry about polar right now, because there's getting involved in polar is actually a different kind of triple integral. So, and we'll talk about that next week. So let's just hold off on polar questions for now. All right, other questions on, so just rectangular, whether it be like, so what would this be? dx, I'll give you one, you tell me what it is. dx, dz, dy. So what type would that be? B. So it'd be B, and then when we get to here, we're doing what? dy, then dz. So that'd be B2, right? Type 2 is where you do horizontal first. You do a typical horizontal strip. What?
Would be dx dy dz then if it's type 2?
dx would be back to front, and then, oh, that is type 1, isn't it?
Yeah.
That is type 1. Thank you. I was just checking it. Yeah, that'd be type 1. And so then if it was dy dz, that would be type 2. That's what I was going for, but I just blew it. So, yeah, dy, I was going for horizontal first. So horizontal then. So now it's type 2. Okay. Questions on the basic? So and we'll talk, I'll do the slide again on Friday, because I think once we do some examples, then we'll go through the slide again and it'll make more sense. Okay. Any questions? All right, let's try an example. Here we go. Okay, so I have a solid. It's my solid E, and it's the tetrahedron defined by these vertices: 2, 0, 1, 0, 3, 0, 0, 0, 0, and 0, 0, 4. So I'll give it a turn here. See it? So can you see the tetrahedron there? It's like a little triangular solid. That's going to be the E, right? So that's going to be, this is going to be the solid E that we're integrating over, right? So it's going to be, so we're thinking about some function of 3 variables, and I want to, this is some like 3-order rate function or something like this, and I want to accumulate my quantity for all points in E, which is this, you're looking at E now. So this tetrahedron is E. Okay, so what I want you to do while I take attendance is I want you to talk through the strategy of finding. One thing we're going to need is we're going to need the equation of a couple of these planes here. So we're going to need the equation of this plane right here. Does that show up as pink, as purple? Pink, blue, and black, that front plane right there. We're going to need that equation. And then red, green, and blue underneath there. See that? There's 2 planes we're going to need the equations of. I tried to warn you that things we did before, you'll need to know at the end of the course. So first think through and talk through what's the strategy for writing the equation of both those planes. And then once you're confident you've got the right strategy with the person next to you, then start doing it, okay? Then we need to find those equations. So you said, say it again?
-3 times x minus 2 plus 6 times z minus 1
Equals?
0.
So then that would be, let's solve for z. Z would equal. No, I'm trying to, let's see. Be, positive 3, so 1/2 x minus 6 minus 12 plus 12 plus 2. Trying to do it all in my head. Minus 6 here. Oh, plus, no, just 0, just 1/2 x. All right, so then that should work for the 3 points that are on it. So how can we test it? Test the 3 points that we know, right? So we've got, what, 0, 0, 0. Does it work? Yes. We've got, what, 0, 3, 0. Does it work? Yes. And 2, 0, 1 is on that plane. 2, it works. So by testing those 3 points, if all 3 of those points satisfy that equation, then we got the right equation. Agree? 0, 0, 0 makes it work. 0, 3, 0 makes it work. And 2, 0, 1 makes it work. So that's the, we're going to call that Z2, because that's the lower one, right? Anyone got Z1? So that's plane 2. You got it?
I got z equals 4 minus 3 halves x
Minus 3 halves x.
minus 8 over 6. That's 4 over 3.
4/3 y. Plus something?
Plus 4.
All right, let's check it. So we got, what, 2, 0, 1 should make this work. 2, 0, 1. So negative 3 and 4 makes 1. That works. Check 0, 3, 0. 0, so 3, negative 0, 3, 0 works. And then this point up here, 0, 0, 4. All 3 points work, so we got it. So Z1. All right, so I'm not going to go over how to do that, but you need to know how to do that. Question?
So, since this, what you call a touch harbor.
Uh-huh.
Yes, I want to call it touch harbor. But how did you determine, like, I know the bottom triangle was the bottom surface,
Mhm.
but which one would you put as the upper surface? Just pick one, or?
Well, we haven't gotten to writing the triple integrals yet, but upper is referring to a higher z value. So which one would it be?
Would it be any of the ones with the 0, 0, 4?
I'm confused about your question. There's the two planes we just found. This plane under here,
Yeah.
that we called, what do we call that? We called that Z2, right? And then this one here we called Z1. So try me again.
If we were to put it into the triple intervals,
We're going to, so maybe, okay,
but like because we have one that's the bottom surface and one that's kind of like the top
Right.
surface. Which one would be considered the top surface?
so top is referring to a higher z value,
Yeah.
and bottom is referring to lower z values. So based on that, which one would it be? Which one would it be the top? Clearly, clearly one of these planes has higher z values than the other. So that would be the top. So which would it be? Exhibit A or Exhibit B would be the top?
Which one was it?
A or B? B. The plane for B has all higher, like if I look down on it, look. So do you see that? So if I'm looking down on it, the top of it is clearly the Z1 plane. And then the bottom of it is that Z2 plane. Does that make sense? Yeah, but that's going to come out when we actually set up the integrals. Yeah, so bottom and top are just in the conventional orientation of R3, where lower would be lower values of Z and higher would be higher values of Z. Okay, so we want to set this up as, let's start with easy, type A. So type A. So what is our mantra for type A? Bottom to top, and then? And then we think about what after that? The projection of the solid into the xy plane, and we do a double integral, right? We do a double integral. Okay, so here we go. So we've got some function f. Don't know what it is. So we're gonna, when you do bottom to top, which variable is that for our inside integral? Z, right? Type A is dz, bottom to top. So this is what we were just talking about. Bottom is going to be, so this is going to be from z, lower z to upper z. So this will be 1/2 x, right? 1/2 x, lower z. 2? Can I just write z1? I'm just going to write z1, which we know is that right there. Okay, and then what do? We take this thing and we project it into the xy plane. Let's give it a whirl here so it looks like what we're used to. And so our outside double integral is for that region. So that's, do you see that triangular region is how it projects into the xy plane? And so what do we need? We need in xy, we need the equation of this line right here. Well, So we got different ways we can do that. We can just, what is this point now? So in x, y, z, what is this point here? What's the x-coordinate of that? 2. So that's 2, 0. Just get rid of the z-coordinate, right? If we're projecting the xy plane, we just truncate the z-coordinate. What's this? 0, 3. It's this point here. Okay? So what is that? So what is that boundary? When we project into the xy plane, that boundary is? Say y equals? Negative 3 over 2x plus 3. So we just got the equation of that line from these 2 points. Okay, so if we do type A1, then we go from, so now we're doing double integral for our region D here, right? Double integral is? So what's our next, if we're doing type 1, we're going to do dz, then dy dx, right? You're using all your expertise from double integrals, dy dx, so y goes from 0 to negative 3 of x plus 3. And then 0 to 2. So there's our outside double integral for the projection of the solid into the xy plane. And we got it. And then the math is just maybe more tedious because you got more variables, but all the rules of integration apply, right? All the same rules of integration apply. Now, with these functions of x, y, and z, you can't just interchange. You can't just interchange dx, y, dz and interchange the things, right? Because these are all dependent on, these bounds could be a function of y and x, these bounds could be a function of x, and these have to be constants. So when you switch things up, those rules, then you've broken out those rules of how that could be, right? So because we have functions for our limits, switching it means going back to the geometry and starting over. Okay, switching the order of integration means reconceiving it. So type A2 that you can do on your own. Should be easy. Now that we've done type A1, okay, you can finish that. So let's skip to type C. And type C would be what? My first variable would be, I'm going to do EY. So let's take a look at that. I wish I could erase some of what I've written. Can't do that. So I'm going to leave it up. All right, so now that means I'm going to do from what to what. And for the y, change in y, it's going to be, our mantra is left to right, right? Left surface to right surface. What's the left surface? Y equals what? So what is that plane? There's a reason we didn't find it, because we just should know it. That plane is? What's the left plane? Y equals what? 0, right? It's just the plane, y equals 0. It's the XZ plane. So just 0. Everyone see that? It's the XZ plane. Okay, 2, y equals? So what am I going to do for this upper bound of integration? Solve this one for y. Solve this one for y. Right? Because it's that plane. Now, see this plane that was the top before in type C is the right side. You see that? So now I'm looking through it, and I'm looking through y equals 0, and then the right side is now what was the top before. Does that make sense? Do you see that? So it's going to be, this upper integration is going to be that same plane, that the big triangular plane there, right there, solved for y. So can I do that fast in my head? No, right, no. Okay, so this is going to be, I'll just write in here so you can do this. This is plane Z1 solved for y. So it's going to be a function of what? X and z. It's going to be y equals something with x's and z's. Okay? And then let's just do type 2. So type 2 will be so now I'm looking at, here's my, so now you gotta get rid of this stuff. So now this is the x-axis, now this is the z-axis, and I'm looking at this thing, and this is this projection into the xz plane. So what about type 2? What happens? Left to right and bottom to top. Comments? Observations? Let's not do that. Why not, Eric? You need two triple integrals. The inside, this is fine. Your inside single integral, the y equals 0 to this thing, will be the same for both. But then we're going to have the double integral is split up. So the type C2 is actually going to be the sum of two triple integrals because that double integral will be just like you've done double integrals. You're going to have to go from here to here as z goes from here to here, and then from 0 to this line as z goes from there up to there. So let's do type C1. This should be 0 to the z1 written as y. And then what will the outside double integral be? So this is what is this the point? For y equals 0, this is the point 2, 1. Right? This is that 2, 0, 1, but 0, but we just truncate off the y because we're projecting into the xz plane. This is the point what? 0, 4. That's this point. And this is 0, 0. So this line is z equals 1/2 x, right? And this is the line. So rate of change is -3/2. Is that right? -3/2 x plus 4. So we're going to go from 1/2 x. So this is our type 2, type 1 double integral. It goes from lower z to upper z. So 1/2 x to -3/2 x plus 4. As x goes from 0 to 2. Remember, this is that z1 plane, but written as y as a function of z and x, right? It's the expression of z and x that equals y. So this order is, what's our order? dy then dz dx.